Hello everyone, more work on applying Newton's laws in this lesson. So we're going to look at a couple examples of Newton's laws in action here, and then we'll continue with the more of the multiple mass system questions. So we're going to look at 3 masses this time, but extending from 2 to 3, and then 3 to 4, and then 4 to 5, and so on. After that, you can just extend to any kind of situation, hopefully. So the CO2 race, this is a tech class favorite at Rideau, where the students have these little cars that they make, and then they have a little CO2 cartridge that they pierce with this apparatus here, and it goes shooting down the hall. And so just we'll watch and see what that looks like. Okay, so why did the car go flying down the hall? Proper analysis would be that there's a force from the car on the carbon dioxide molecules going like this way towards the pants of this person here, towards the leg. And then the reaction force, the force of the the CO2 molecules on the car, that's the force that accelerates the car forward, right? Okay, so force backwards on the CO2 is the applied force, the action force, and then the reaction force is of the CO2 molecules on the car. That's what makes it go. Okay, there's really no other way to actually analyze that. The physics class version is these ones, where we get a fire extinguisher out here at Rideau, and we do that kind of thing. So this is so this student explains the physics of it, and then having successfully explained the physics, is allowed to go ahead and do this. Obviously, a lot more mass being a whole student on a skateboard and whatnot than the little car, so it doesn't go as fast. She also didn't, she was not being greedy there. She didn't squeeze it for very long. And then a second student got to have a chance as well. But again, force of the fire extinguisher from the pressure on the CO2 molecules. This is a carbon dioxide fire extinguisher. Definitely the custodian in my school actually was very concerned that it wasn't just carbon dioxide, it was going to make a mess. And I was like, no, seriously, it's okay. Look, it says it's, and sure enough it was. Thank goodness, otherwise I would have been in trouble. Anyways, so yeah, force on the carbon dioxide is the action force. Reaction force is carbon dioxide on the system here, making the acceleration go down the hall, right? So that one, and then there's another one here. Same idea. Full Rocket Man mode. And then eventually hits the wall and falls over and everything else. But yeah, understanding Newton's third law is necessary to describe those situations. All right, multiple mass systems all ready to go here. We have 3 blocks this time. We're pushing at 100 newtons on a 20 and a 40 and a 5. Forces transfer between. We've got the force of the 20 on the 40 here, and the force of the 40 on the 5 here, labeled, and so on. So what are some steps that we're going to go through for this? Obviously, the first main step is to notice that you kind of want to determine the acceleration of the whole system. And so, look at the net force and the F net equals ma. Maybe I'll just go through this as we go here, but I kind of want to give you an outline of it. I'm not sure if it makes sense to do that or not, though. Maybe we'll come back to it. Okay, so let's just go through it as we go. And we'll do a summary afterwards showing like all these steps and how they all made sense. Okay, so determine the acceleration on the system. Well, F net equals ma, of course, right? And in this case, we've got a grand total of 65 kilograms. And so I have to add all those up. We have our net force on the system is just the 100 Newton force, right? So as a separate thought, you could definitely think of like net force is always the sum of all of the forces. It's just that there's only the one, right? We don't have these other ones to worry about. So we get that net force of 100, and the number then we can calculate out by just dividing both sides by 65, and we get the acceleration of the system will be 1.54 meters per second squared. Okay. Our next key step is to recognize that if the whole system is accelerating at 1.54 meters per second squared, then each one will be accelerating at that same amount. Okay, so if we look at, I deleted by accident. Here we go. So if we look at each one, we can use the fact that acceleration of each block is going to be the same as the acceleration of the system, like I said, and we can get the net force on each block. Because if we know acceleration, you can get net force, right? So we know acceleration of 1.54 and the mass, and same thing all the way along for these. You can get the net force on each block. Okay, the net force has to be 7.7 and 61.6 and 30.8 in order for the 20 kilogram to accelerate at 1.54, and in order for the 40 to accelerate at 1.54, and so on. Okay. So the next step is going to be to say, well, if we know the net force, the one I'm going to pick on here next is the 5, because it's the easiest. There's only the one force on it. If I know the net force on it is this, then I can talk about, what the force is between these two. We've actually isolated out to see what this force of the 40 on the 5 really is. It's going to be the 7.7, obviously, right? So how I'm going to show that is we can look at that contact force. We're going to look at the 5 kilogram block next on purpose because it has the least forces on it. So it's nice and simple. And yeah, that contact force is that net force, right? So we have the net force on it is, a bunch of stuff added up, but really there's just the one, right? There's just the 40 on the 5, 40 kilogram on the 5 kilogram. So we know that force is 7.7 from the previous page. So that means we know the net force on it is, equal to the applied force. So really we know that 40 on 5 force is 7.7. Okay. This other part here, we have to recognize that for every action force of 7.7 forward on the 5, there's going to be a reaction force backwards, right? So there's going to be a reaction force backwards, the 5 on the 40, of negative 7.7, or in other words, backwards. Okay, that's a third law reaction force. Okay, so that's going to set us up to have information about the force on the 40 kilogram block, right? And so on and so on. We'll keep working our way through. So the next one, the contact forces, let's go to the 20 kilogram block next, because we have information about it. We got the 100 directly on it. We don't know this force, right? And so I think we could probably get it next, but it's just a sequencing of things. Like we couldn't start with the 40 originally because we don't know either of these forces. So all we know is the net force of whatever it was back here, the net force of 61.6 would be made up of these two forces added up. We don't know either of them. Right? So you don't want to start with the 40, that's for sure. I started with the 5. I could have started with the 20. So I'm going to that 20 next, of course. So we got the net force on it is the 30.8 that we calculated before. The net force on it is made up of two forces this time. We've got the applied force and the force backwards on it from that. That's your reaction force. Okay, so see how the third law carries us through this, where we can actually talk about action forces and reaction forces, and it's necessary. If you look at the free body diagram for the 20 kilogram mass, we have an applied force on it and a force back on it, right, from the 40 kilogram. So we have numbers for the applied force and the net force, and so it allows us to solve for that mystery force of contact between the two. Okay, so we get that it's a force of 69.2 newtons backwards on the 20 kilogram block. And of course, we have the reaction force stuff, right? And so if the force on the 20 is backwards of 69.2, then the force forwards on the 40 is the positive, right? So this is just Newton's third law in action here, where it's just the opposite of the force, giving us that forward force. Okay, and then press pause as needed to slow this down, of course, but I'm just, it's a video. You can slow things down if you need to, or speed it up if you'd like. The final step here is we can look at that 40 kilogram block, and we know stuff about it now, right? So we can say, oh, well, we know that the forces on it add up to the net force. We know the net force itself. Well, actually, there's multiple ways to check this, so I'm just going to do this. I'm going to say, okay, they add up to 61.5 newtons. The net force on it of 61.5 should match what the net force is for its motion. And I think maybe we already had that anyways, didn't we? That net force of 61.6, right? So within rounding errors here, we're getting that same net force. Okay. The other way to do this, I'll do it in the next question, the next version that I'll show for help, is we could have calculated out what this net force leads to as an acceleration. And of course, it should match the acceleration of the system. That's it. So this is just the way I checked this time, is to see if the the net force matches what it should. I just don't like that I calculated that again because we already did calculate it. So just be clear on what you need to do at each step, I guess. And then this idea here is an extra question that obviously would have to be asked to bring you to prompt you to do this. But if you look at those forces, the 69.2 and the 7.7, it says like which contact force is bigger and why. Well, we can certainly analyze that this one is bigger because it needs to be in order to provide the force, right? To push and accelerate all that weight, all that mass, I should say, right? So I put in there, it's larger since it needs to provide the force needed to accelerate the 40 and the 5 kilogram combined. There's two ways of talking about why this one's smaller. Okay, so one is matching, where it's like, oh, you don't need as much force because you're not accelerating as much mass. But a different way of thinking about it that has some value is to say, okay, well, that force here, you can think of that applied force of 100 newtons as some of it got absorbed by this 60 kilograms, right? So you can think of it as the 20 kilogram and 40 kilogram force masses. Kilogram. I need to reword this here. You can also think of a 20 kilogram and 40 kilogram masses as effectively having absorbed a lot of the force. Okay, and that's inertia, right? So it relates back to the first law. And so, like, you see something like this, like, why do metal workers have anvils, and this person has a counterweight here for their bench grinder on a portable stand, right? Obviously, the counterweight is a good idea, but also if you're trying to hammer something straight, you put it against that and you hit it with a hammer, and things don't go anywhere. Things don't move because this thing is very, very, very has a lot of mass, right? And so if it has a lot of mass, it has a lot of inertia, and so you can hit it and it doesn't accelerate off, and tip this thing over and so on. Okay, so that little anvil type thing there, it looks like a section of a train track, I'm guessing. It helps absorb that impact force. Okay, that's the concept I'm trying to get you thinking about in the way I've analyzed this, especially this last one. All right, so what about if we're looking in the vertical direction? That means we have gravity to contend with. So these gravity forces are just given to you. We're going to be able to calculate those later on. Okay, so the plan for this thing should be kind of similar, right? Get the net force on this system, right? Get the acceleration of the system. The acceleration of each block is then known, and then you can start to analyze what the forces must be at each spot, and so on, and so on, and so on. So I think maybe this one might be the one we tackle first, right? Because if you end up knowing its acceleration and you know the gravity force that's on it, then we'd be able to figure out that missing applied force up. These are attached together, obviously, here, right? By strings or welded together or whatever, right? Little connectors. I should have pointed that out. Should have had them like this, I guess. Little strings in between. I knew what I meant. But yeah. A little, not letting me do it. Little string, little string. Right? So these guys are attached. Artboard is giving me a hard time. All right, that's attached. That's attached, obviously. Okay, so those forces, what kind of forces do we have in the middle and so on. So very similar plan last time. We can get the net force on the system. The only difference is there's three other forces to talk about, right? We've got the forces of gravity, but we also have that applied force up. So grand total there of negative 37 newtons. What that's meaning here, I did this one on purpose this way. The one in the homework will be the simpler one where you're actually raising it up. But we're trying to lift this, but we're not strong enough, right? So it's still accelerating down a little bit. Okay, so we're trying to lift this thing, but it's still falling, but it's certainly falling slower. Okay, so that could actually be the down motion when you're working out. You're applying an upwards force and allowing it to lower slowly, right? Working out at your muscles as you're doing that. Okay, the one in your homework has a bigger applied force than the gravity forces, so it's accelerating up. I think that's probably the easier one to kind of analyze. So I tackled the weirder one in class here. So the net force equals F net equals ma to get the acceleration, as always. So we have the negative 37 equals the grand total of the 65 divided out. We're ending up with this downward acceleration, right, of 0.569. Okay? So that's down, obviously. Like I said, it's lowering a little bit, lowering slowly, speeding up as it lowers, I suppose. But I guess in working out, you'd probably lower it at a constant velocity. But anyways, we'll get to that later on. So same kind of deal here, right? For each one, you can get the net force, right? If you know the acceleration, you can get the net force. So it's simple calculation, just the mass times the acceleration. Each one, we have the net force on each one. So don't cloud your judgment here. Like, yeah, there's more than one force on each one of these things and so on, or on some of them, but you don't have to worry about that for now. The net force is just the net force. I kept extra digits as I went along the way here. Technically, like if we're keeping 3 significant digits, I should have probably rounded that. But well, if this was my final answer, I would round it. But engineers and proper work is really just to float decimal places, carry a bunch all the way through. So even actually at the beginning here, this 0.569 number, but I could have, if I was an engineer, I would keep more, right? Use a computer program to keep track of this. And I did the wrong thing there, but the 37 divided by the 65, we have this number, so just carry that number and you'll have more accurate work. And then you just round the number you can trust in the end, right? Anyway, so those are net forces. Now, each one, when you're analyzing, so let's pick the 20 because it has just the one force on it, or the one pull force on it. The 40, for example, is going to have a pull up, but it's also kind of a pull down, right? So it's a little more complicated. You can't start with the 40. You could have started with the 5, though. So this one, though, if we're starting with the 20, our net force on it is going to have, of course, the force upwards of the 40 on it, and it's going to have the force of gravity on it. Okay. First time running through this solution, actually, I forgot to add the gravity, and the numbers just weren't making sense. The force here was actually down on this object. I was like, what? And so I went back and remembered, oh yeah, I got to include that gravity force, right? The net force we already know from the previous work, right? The 11.38 newtons down. So we're just going to add 196 to both sides, and we'll get the force of the 40 on the 20 is 184.62 newtons up. Okay, helping lift it, but allowing it to still accelerate down, right? And on top of that, while we're at it, we may as well notice that if the 40 pulls up on the 20, then the 20 also pulls down on the 40. Okay, Newton's third law. That'll be necessary when we go to analyze the 40 kilogram object, that is. All right, so next step here, we've got what? If I go to the 5 kilogram block next, right? Could have started with it. We've got the net force on it is known. The applied forces on it are some things that we know some of, at least. We know the applied force, we know the net force, and we know the gravity force. And so, of course, we can figure out the missing force of the 40 down. So I'm just going to add 49 to both sides, and I'm going to take away 600 from both sides, getting the force of the 40 on the 5. Okay, obviously the 40 on the 5 is pulling down, right? If you had a positive there by accident, you probably made a mistake, right? Definitely made a mistake. So obviously Newton's third law, if the 40 is pulling down on the 5 conversely is pulling up on the 40. So now we're ready to analyze that 40 kilogram mass. We've got lots of forces on it. We've got the force of the 5 up on it, the force of the 20 down on it, and the gravity force. We can itemize those all out and say it's got a net force of 22.775, which is, if we look at that 22.775, we've to the second decimal place, we're the same, right? So that net force right away is actually a confirmation itself. So same as previous step. I just didn't notice to point that out. And if you wanted to do another check, you could say, well, what kind of acceleration does that net force cause? And you'd see like, oh, 0.569, that's the same as the group. So of course things are making sense. Okay. So hopefully that's making sense to you. This is a trickier thing to try to tackle on your own from scratch. I hope I've done a thorough enough and good enough job showing you like the idea of sequencing here. Look at things you can solve as you go through it. So you've got one to practice here of a sideways push, and then a pulling version of it. So it actually kind of effectively, well, I'll let you run the numbers. And so it's the same question, same set of questions here, and talking about which forces are bigger and so on. It's a little tiny there, but the same stuff as this. So, I said I was going to do the summary here, right? So the idea of, use the fact that get the net force on the system, and then get the acceleration of the system, and know that each part is the same acceleration. And then the simplest block to deal with, because there's the least forces on it and so on. But don't forget to point out that Newton's third law reaction force, and then tackle the next block that's easiest to deal with, to the 20, get the contact force between those, and so on, right? We're going to use that net force on the 20 to be able to figure out this unknown force. And then finally on the 40, you now have all the forces that are on it. And so you can either add up, see if the net force is what it should be, or you can see if the acceleration is what it should be, and so on. All right. Yeah, so that kind of worked for both of those. And then you have the gravity, including gravity version, where we're pushing up from the bottom. Right? And so same kind of work here, obviously, right? So the main question is to, determine the forces between these things, but, determine showing your work and so on, of course. All righty. Stuff. All right. Thanks for watching. And if you need any help, don't be shy. Let me know. No one's been using the post help questions thing lately, so it'd be nice to see some questions posted in there so people can get help from your question as well. So anyways, talk to you later. Thanks for watching.